Hi, in this video, we're going to talk about simultaneous equations and the relationship to geometry. So here I have three cases here with the example for each case. So you can see here I have an equation 2x plus y equal 5 and x minus y equal 4. So what does that actually mean in terms of their geometry? So think about if one line that go like this. So this line can be 2x plus 5, y equal 5, right? And then the other line, if I sketch a linear line, it looks like this, x minus y equals 4. So you can see that they actually intersect at one point here. So we call that a unique solution. And when you solve simultaneously, you're going to end up having x equal 3 and y equal -1, which is the coordinates of this point right there. Okay. So what does that mean when they have two lines meet at the same point? If you rearrange this one to make y as a subject, so in here y, I want to solve for y, so I'm going to move the y here and I move the 4 to the left-hand side, and we have x minus 4. So you can see the gradient equal 1 here, okay? And if I do the same for the second equation, I have y equal, so I move the 2x over. So I have negative 2x plus 5. So what I can see here is the gradient equal -2. So the moment that they have different gradient, so if the gradient here is different from the gradient here, then they will meet at a point. Now, if we continue analyzing the second case, we're going to see the gradients if they parallel. So doing the same thing. So case number 2, I have this equation, 2x plus y equals 5 and 2x plus y equals 7. Let's do it here. Now, if I rearrange for y, I move the 2x over, I will end up having y equal -2x plus 5, right? And if I do the same thing here, I rearrange, I move 2x over, I got y equal -2x plus 7. Now, if you sketch these on the Cartesian plane, you can see that the set equal 5 here and negative gradients, so the line will going down like this, okay? So this is y equal -2x plus 5. And I do the same thing for this one. So for the second graph, y will be equal 7, and your graph will go negative, so it go like that, going down again with the same gradient. So in this case, we call that a parallel line. So these lines are called parallel. And because they're parallel, they will never cut each other, so you end up having no solution. So how do we know if there's no solution or not? What we do is we look at the gradient. So if the gradient are the same, but the y-intercept, so we look at the y-intercept is different, okay? So M1 equal M2, but C1 equal C2. All right. Now, the last case is infinite solution. So if I do case number 3, if I rearrange for y here, I move the 2x over, I will have y equal -2x plus 5. Then I do the same on this. I move the 4x over, 2y equal -4x plus 10. And then to get the 2, I divide it by 2 on the other side. So I will have y equal -2x plus 5. So you can see that this equation, the first equation, is exactly the same as the second equation. So what does that mean on the graph? Technically, they are the same line. So think about you have the 5 at the y-intercept, the line going down. Okay, this is for the first one. And then the second one is pretty much the same thing. So they basically just overlap each other. So because they overlap each other, you will have all the points infinitely lies on those one line, one identical line. So we have infinite many solution. Okay, so basically they're the same line with the same gradient and the same y-intercept. All right. Now we're going to make a summary of all these cases. So the question is, how do we know if the two lines are no solution, infinite solution, or um, unique solution? So we're going to generalize into y equal m1f plus c1 and m1 and c1. M1 is the gradient of the first line and c1 is the gradient of the second line. We're going to call that line number one. Okay. Then line two, we're going to call that y equal m2x plus c2, the second gradient, and the boundary set, the second line. So if they have a unique solution, so unique solution means they're going to cut each other like that. So for that to be happen, m1 have to be equal m1 not equal m2. So they have different gradient, m1 not equal m2. Okay. Now, if I have no solution, so when I have no solution, the line will going to be parallel like this. So they never cut. So for that to be happen, m1 equal m2. So they have to have the same gradient, but the set have to be different. Okay, C1 not equal C2. And the third case is if you have infinite many solution. So for many solution, one line is here and then another line is just on top of it. So they are identical. So for that to be happen, M1 equal M2, same gradient and same one set. So everything is the same. C1 equal C2. Okay. So we're going to apply that to answer these questions. Right. So here they say explain why this equation and this equation have no solution. So to have no solution, they have the same gradient but different one set. So to show you working out, you're going to rearrange for y first. So here I do this one first. So here I move the 2x over. So I have, let's do again, 2x plus 3y equals 6. Then I move the 2x over by taking away 2x, so 3y equal negative 2x plus 6. Then to get the 3, you're going to divide by 3. Divide by 3, divided by 3. So the 3 and the 3 will go away. Okay, so you will end up having y equal negative 2x over 3 plus 6 over 3 is 2. And then I do the same for the second equation. So I have 4x plus 6y equal 24. I solve for y by move 4x over, so 6y equal negative 4x plus 24. Then I divide it by 6, divided by 6, divided by 6. 6 and 6 go away, so I have y equal negative 4 over 6 is negative 2 over 3x 24 over 6 is 4. So here I can look at my gradient. So you can see the gradient of the first line is negative 2/3, and it's the same as the gradient here. So that's M1, that's M2, M1 equal M2. But see, you can see the one-intercept, you can see the one-intercept here equal 2, but the one-intercept here equal 4. So we explain that M1 equal M2 equal negative 2/3. They have the same gradient, okay? And C1 is not equal C2. So C1 is 2, does not equal 4. So they have the same gradient, but they have different one-intercepts. So therefore, they are parallel. And because they're parallel, they have no solution. So they don't cut each other. All right. Now we're going to learn describing infinite solution using parameter. So what is the parameter? Parameter is when you have to describe an infinite solutions like the two equations, okay? And because there are too many solutions, we use a letter, and that letter we call parameter. So it think about that like a constant, but it can have different many values depending on what you want, because you have infinite many solution. All right, so let's do this example. How do we describe it? So our first step is, so we already told you that it have infinite many solution, so you don't have to check that. And now describe the solution using parameter. So the first step is you can let x or y equal a parameter, and parameter is usually a Greek letter, so we can call that, let's call that alpha, okay? Now, or you can do y if you want to, you can say y equal alpha, it doesn't matter. Then step 2 is you're going to sub x equal alpha into either equation. You can sub into here or here, you will end up having the same answer, okay? Just one equation is enough. I'm going to pick the first one. So my equation is 2x plus 3y equals 6. Now x equal alpha, so I'm going to substitute alpha in here. So I have 2 alpha plus 3y equals 6. And then from here, I'm going to solve for y, right? So to solve for y, I move the 2 alpha over. So I have 3y equal negative 2 alpha plus 6. And then you divide it by 3, divided by 3 on both sides. So 3 and 3 go away. I'm going to drop this on now. And you will have 6 divided by 2 is 3. So you can see that therefore the solutions, the infinite many solution that you could have is x equal alpha, as you can see here, and y equal negative 2 alpha over 3 plus 3. So this equal describe the solution using the parameter. So alpha can be anything you want. So let's say alpha equal 1. Okay, so if alpha equal 1, then x will be 1. And y will be negative 2 third times 1 plus 3, which give you 7 over 3. So for alpha equal 1, you get a solution for x and y. But if you change alpha equal 0, you're going to get a different solution for x and y. All right, so you have infinite solution for that reason. Different alpha value will give you different solution. Right. And to solve this on the CAS, you can go to menu algebra, solve system equations, and then put the equation in. You have two equations here, comma x and y, and it gives you the infinite solution like that. So if you can see, they have C1 here. So C1 is basically alpha. So they're telling you that x equal negative 3 bracket alpha minus 2 over 2. And you can see they do comma C1, so that's the y equal alpha. Good. All right, now come to the most important part of today's lesson is you're going to use the knowledge of unique null solution or infinite solution to find the unknown value like this. So these are usually typical exam questions. All right, now we're going to do an example here first, and we can summarize the step. Here I have considered two equations, and I don't know m and k. M and k are the constant, and you can see x and y right there. Now find the value of m and k shows that the system of equation have a unique solution. So we talk about to be a unique solution, they have to cut through each other. So for that to be happen, M1 have to be equal M2. Okay? No solutions, M1 equal M2 and C1 not equal C2. And then infinite solution is M1 equal M2, C1 equal C2. Right? So C2. So your first step before you do anything with these type of questions is you're going to need to make Y as a subject first. So you need to find what is the gradient and what is the y-intercept. Okay, so if I go back to my step here, step 1, I'm going to rearrange to make y as a subject, to make y equal mx plus c, right? And then depend on the information. If you have a unique solution, then m1 not equal m2. If you have parallel, and we say m1 equal m2, c1 not equal c2. And if you have one line and you have another line on top of it, and then you will have m1 equal m2 plus c1 equal c2 as well. Okay, and then your last step is you're going to solve for the constant, solve for the unknown based on what you have in step 2. All right, so we're going to put that in here. Our first step is we're going to rearrange to solve for y. Okay, so I start with the first one, m minus 2x plus y equal 2. If I make y as a subject, I'm going to move the whole thing to the other side. And because it's a plus, and opposite of plus is minus. So think about you minus the whole bunch of things to this side. So you will have y equal negative m minus 2x plus 2, like that. So you can see this is my gradient, the number in front, the coefficient of x, that's my gradient. And this one, 2 with my y-intercept, okay? Then I do the same thing for the other equation, mx plus 2y equal, okay? So I'm going to move the 2mx over, so I take away mx. So 2y equal negative mx plus k. Then I need to get rid of the 2, so divided by 2, divided by 2, divided by 2, and 2 and 2 go away. So you will have y equal that, negative mx over 2 plus k. So what we can see here is, we can see that's the gradient, yeah, and that's the y-intercept. All right. So a unique solution. So let's do question A. Unique solution is m1 not equal m2. So m1 is the gradient of the first one, which is this. So negative m minus 2 not equal m2 is negative m over 2. So from here you can just solve for m. Because they both have negative and negative, you can cancel them. So get rid of that. Okay, so no more negative on both sides. Then you can multiply the denominator over. So 2m minus 4 not equal m. Take the m over, so 2m minus m not equal 4. So m not equal 4. So to answer question A, find the value of m and k, show that the system has unique solution. So to have unique solution, m just not equal 4. So m can be anything, just not 4. Or you can write m is r, everything excluding 4, like that. Doesn't matter about k. K is not important in question A. All right, B. If I do B, I pretty much do the same thing. So for B, I want no solution. So m1 equal m2 and c1 not equal c2. Okay. So m1 equal m2. We talk about m1 is the gradient here, negative m minus 2 equal m2 is negative m over 2. And c1 is 2 not equal k over 2. And from here you can solve it. So this is pretty much this I on the left hand side. So instead of not equal is equal. So you do the same thing and then you will have the whole process again and you end up having n equal 4. Okay. And 2 times 2 equal 4. So k just not equal 4. So for B, m equal 4 and k not equal 4. So k have to be something else. All right. Then we have a unique infinite many solution. So to be infinite many solutions, M1 equal M2, but C1 also equal C2. So say we have M1 equal M2 and C1 equal C2. Okay, so negative M minus 2 equal M over 2, and C1 is 2 equal K over 2. So we have K will be 4 here, and here we already solve it, which is on the left side, we get M equal 4. So M equal 4 and K equal 4. That would be C.